Good morning, everyone. And soon I will share screen. Okay, I hope all of you can see this. So we were talking about stationary distribution and limiting probability distribution. And after the definitions, we had proved this theorem. If pi is a limiting probability distribution for the Markov chain, then whatever may be the initial distribution, that is whatever may be the distribution of x0, the limit probability xn equal to y is pi y. And also in such a case, pi is the unique stationary probability distribution. The limiting distribution is a subclass of stationary probability distribution. So uniqueness is asserted in a larger class. So this theorem we had finished proving. Yeah. Right. And this is where we had stopped. Okay. Today we will look at two examples, rather one example completely and another example partially. So this example is same thing as a question in one of the problem sets. So this example is going to be a case where the stationary probability distribution is unique, but it is not a limiting probability distribution. So let P be a number between 0 and 1. And Xn be a Markov chain with this state space is a 3-point set, 1, 2, 3. And the transition probability matrix is given by this entry. So for our discussion, you can note down this matrix in a piece of paper or something like that. So this 3-point state space, you can also observe that states 1 and 3 are reflecting boundaries. And of course, you can easily see that it is an irreducible Markov chain and also a recurrent Markov chain. Of course, I expect you to supply the reason really. So you may note down this. Yeah. Now let pi, which is stationary probability distribution of the Markov chain. So that is going to be a probability measure on this 3-point set. And the probability of the singletons, we are denoting it by pi 1, pi 2, pi 3. So now we will write down the system of equations briefly. In that you should remember that this will be treated as a row vector and you have a matrix here. So pi 1, pi 2, pi 3 varies here. You will be doing the multiplication with the terms in the column wise here. Okay. So if you do that, you will see that pi 1 is equal to summation over I going from 1 to 3, pi I, pi1. K will be 1. And similarly for pi 2, pi 3. So you will get a system of 3 equations together with the constraint that these pi i's should add up to 1. They are all, of course, non-negative. So you have a system of 3 equations and a constraint. Constraint, of course, you can also include pi k greater than or equal to 0 is also a constraint. So it is quite easy to solve this equation, especially given that this P has this nice form. Note it down if you want to. So I leave it as an exercise for you, solving the above system of equations that is corresponding to KU equal to 1, 2, and 3. And using the constraint, you can see that pi 1 is half of 1 minus P, pi 2 is half, and pi 3 is half of P. It's a very simple exercise to do. Yeah. What this shows is, see, we are a priori assuming here that pi is a stationary probability distribution for the Markov chain. So this means if a stationary probability distribution for the Markov chain exists, then it has to be this. So this proves uniqueness of the stationary probability Markov chain. If there is a Markov chain, it has to be this. There is no other choice. Now, in this context, showing the existence is very trivial because let's say we have got this candidate. You just have to see to it that this candidate solves the equation. So easy to verify that pi 1, pi 2, pi 3, which is given by this, is actually a stationary probability distribution for the Markov chain. So it follows that the Markov chain Xn with P as its transition probability matrix has a unique stationary probability distribution. Please note it. So for example, if you are able to guess it by somehow, this could be a formula, and you throw it, it is actually a stationary probability, then that means a solution exists. That is, there is a stationary probability distribution. And then the other proof will take over. If there is a stationary probability distribution, then it has to be this. So for this Markov chain, there is a unique stationary probability distribution. Okay. Now you are given this matrix P, and you can easily find out P squared. So those of you who have done that problem would realize this is P squared. And if you have done that problem, you would also have verified that Pn is same as P if n is odd, and P squared is, sorry, Pn, P to the power n is P squared if n is even. So I hope all of you have done that and found it. Now you notice something in P and P squared. In P, all the diagonal entries are 0. However, in P squared, all the diagonal entries are strictly positive. And also, we have found that P to the power n is P if n is odd, and P to the power n is P squared if n is even. So there is no way this will converge to the same limit. For example, P to the power n, the diagonal terms of P to the power n will never converge. So it is easy to see that there can be no limiting probability distribution for Xn. So existence of a unique stationary probability distribution does not imply existence of a limiting probability distribution. Please note it down. If you want me to go back to any of the previous slides, please tell me, I will do it. Okay, let us go to the other example. So in the next example, we will be, in that case, the stationary probability distribution is also the limiting probability distribution. This is also a question from problem set. It is called success runs Markov chain. So that is, if the, let us say P is the probability of success in some experiment, or maybe even tossing a coin, which has probability P for head. And you keep on tossing as long as you run through heads, or rather successes, that will count the number of successes. Once a failure comes, that thing will come back to 0. Suppose first 10 tosses are success. So for X1 will be 1, X2 will be 2, and X10 will be 10. And 11th one is failure, then X11 would be 0. And after that, X12 will be 1 if the 12th toss happens to be, 12th, this thing happens to be a success, and so on. So the success runs of Markov. So in this case, the transition probabilities of the Markov chain are given by probability of going to state I plus 1 from I in one step is P. Probability of going to 0 from I is 1 minus P for every I. And of course, Pij is 0 otherwise. So from any state, in one step, you can go to the next higher one or 0. These are the only two possibilities. Note that Pi0 is 1 minus P for every I. Therefore, in that matrix, the first column, that is the column corresponding to 0, will all be 1 minus P. Of course, you can easily see that the Markov chain is irreducible and recurrent. Or it is probably part of the exercise, this question. So we will sort of write down that matrix because since we will be coming back to it. So as I said, this, when you do that multiplication of pi I, pi, k, you will be running down this kind of things, running down the columns. So this column corresponding to 0 is all 1 minus p. The column corresponding to 1 is the first entry, that is corresponding to 0th row, the row of I, that is p. All the others are 0. So note that this is P01, capital P sub 01. And similarly here, this is capital P sub 1, 2, that is P. All the other entries in this column are 0. And so on. Please note it down because you may have to sort of take a this thing at it as we proceed now. Okay. So if a stationary probability distribution pi exists, so see this if, so assuming that this pi exists, then for each j varying over 0, 1, 2, pi sub j is summation I going from 0 to infinity, pi I pij. And of course, all these things, pi j's have to be non-negative. And this should add up to 1. So now let us try to solve. Okay. The equation for pi 0, just. Yeah. So on that as a left vector, row vector, it will be pi 0, pi 1, etc. you will be having. So when you take the sum, pi I, p, capital P, I0, and p I0 is 1 minus p for every I. Consequently, you have this. And the term corresponding to I equal to 0 we separate. So that is pi 0 times 1 minus p. And the other things, so this is 1 minus p for every I. So that comes out of the summation. So you have summation I going from 1 to infinity of pi I. And because of the constraint, summation over I going from 0 to infinity of pi I is 1. So therefore, this guy is 1 minus pi 0. So you get pi 0 equal to pi 0 into 1 minus p and 1 minus p times 1 minus pi 0. And that immediately gives you pi 0 is equal to 1 minus p. Please note it down if you want to. Okay. Let us go to the next one. Now we consider the equation corresponding to, let's say, j greater than or equal to 1. So again, we go back. So it will be the pi summation will vary over pi I times Pij. So the corresponding to j equal to 1, you have only this entry contributing something. And that will be in terms of the pi in the previous step. Yeah. So this is summation over I going from 0 to infinity, pi I Pij. Now Pij is 0 except for I equal to j minus 1. So the only one term survives there. So this is pi j is pi j minus 1 times P, capital P sub j minus 1j. And this term we know is P. So you have pi j equal to P times pi of j minus 1. So you can compute pi j if you know all the pi's up to j minus 1. So we have pi 1 equal to P times pi 0, and pi 0 we already know. So it is P times 1 minus P. And pi 2 is P times pi 1, so which is P squared times 1 minus P. So going similarly, pi k is 1 minus P times P to the power k. K running over 0, 1, 2, etc. So each pi k is strictly positive, and also they add up to 1. So what this means is, if there is a stationary probability distribution, then that is given by this. Yeah. So verifying this is very simple. Use the geometric series. And it is an easy exercise to verify that pi given by this formula is actually a solution, is actually a stationary probability distribution. So we will show, actually I had sort of underestimated. I thought won't be able to cover that also in this class, so I didn't prepare slides for that. Anyway, so that means today we have a light class. So that pi given by this formula is actually a limiting distribution. So we will take it up the next one.
So is today's lecture over?
Yeah, it is. It turns out to be. See, I took a long time to prepare this slide, and also longer time for the next part. So I thought there were about 25 slides today, but seemed to go off smoothly, much smoother than I had expected. If you want me to go back to any of the slides, please tell me.
Okay, so today's class is much shorter.
Yeah.
Okay.
Usually I go for about 40 minutes, but today it is just about 30 minutes.
30 minutes. So what will you do in the next class? That is in Wednesday.
Wednesday, I will first show this. And then I will state one theorem, but before taking up the proof, I want to sort of tell you certain things.
Okay. Okay.
So that is how to go about giving conditions for the existence of a stationary probability distribution and uniqueness and so on. And also the, what is it? When will you have limiting probability distribution? So for example, to take up that question first, in this second example, which we got here, where is the matrix? Yeah. We look at this matrix. Okay. So in this example, the stationary probability distribution exists, and of course, and it is unique, and also it is the limiting probability distribution. If you have noted the matrix down, keep it separately. And the first example, look at the matrix. Do you sort of sense some difference? Of course, one is finite and another is infinite. That is not the thing. Yeah, especially look here. Is there some striking feature here? Any of you? I mean, it doesn't matter if you make a wrong guess. So anybody wanting to hazard a guess?
So basically in this matrix P, only the second row is dependent on the parameter P. But the first and the third rows, they are independent of the parameter P.
Sure, but the thing is, when you take P squared, that is sort of reversed, right?
Yeah.
Okay. No, I think that is not the, well, that is not the Quizmaster's answer. Anyone else? Come on. Let it not be only Aranya who is doing the talking from your side. Okay, let me give you some kind of a hint, kind of returning to the starting state. See, both the cases we have considered, the Markov chains are recurrent. Okay, right? In this, it is a recurrent Markov chain. The other one also, it is recurrent. All right. So when there is recurrence, there is a return to the initial state with probability 1. There is the probability of returning to the initial state is 1. So now give that thing, do you see some difference? Yes, anyone? Okay, if you start from, let us say, state 1, how many steps does it take to return to state 1?
I think it will be even number of steps.
Even number of steps, very good. Which means you cannot return to the state in any odd number of time, odd time point, right?
Exactly, yeah.
So there is a certain amount of periodicity.
Okay, so that means starting from state 1, it can return to 1 either after exactly 2, 4, 6, 8 steps, something like.
Yes, that is, if you consider all those n's for which, let us say, if you start from state I, probability xn equal to I, all those n's, that would be the even integers.
Okay. So probability xn equal to I is positive.
Yeah, but yeah, probability xn equal to positive. Yeah, correct. You are right.
So yeah, then n will be.
That is true of any of these states. Okay. So this is a case of a Markov chain with period 2. What about this guy? And also we will prove that in an irreducible Markov chain, if one state has period k, every state will have period k.
So this happens for an irreducible Markov chain, right?
Irreducible, because the periodicity is maintained. I mean, that is so same for all the states in that period, and in that irreducible closed set.
Okay.
So if the Markov chain is irreducible, the whole. See, take here, for example, 0. From 0 to 0, you can come back in one step because the very first step happens to be a failure. You can come back in 2 steps. So you can go to P, that is the first step, then and then next step, if it is a failure, you can come back to P. So here, sometimes you may not be come back in the very next step. Let's say about 3-4 steps later, you can come back and again and again, or something like that. Okay. So this is the case of an aperiodic Markov chain. Of course, the periods, etc., we have to define very carefully, rigorously. So in the aperiodic case, you will have, with of course certain other properties conditions also we have to put. Certainly one has to put recurrence and so on. We'll
So
have to
basically, in this case, one can mean starting from the ith state. In one step, either one can go to I+1 state or to the first state.
zeroth state.
Zeroth state, yeah.
Yeah. Okay, in one step, you can only go one step forward or just back all the way to zero.
Back all the way to zero, yeah.
Okay. So the aperiodic case is the one where there will be a, assuming that other conditions are also satisfied, that would be the thing where you will have limiting distribution.
I think, sir, you gave this example in problem set 2.
Yeah, that's what I told you here.
Okay. Yeah.
Even when we started example 2, I had said that. Okay, so if there is no further question or anything, we will end the session today. Yeah, it's maybe in a good way that the things ended about much in advance. So you have some questions to ask out of curiosity or something like that. Others also, please just don't feel shy. Okay. See, if you happen to make a wrong guess or a wrong answer, even then your knowledge improves, that at least you know that that particular guess or answer is incorrect. I think one should not be afraid of making mistakes. I do make a lot of mistakes. You might have seen with many other teachers also. There is always the saying, no, to err is human. Okay, if there is no further thing, we can sort of end the thing today. Again and again, I keep repeating, seeing the same names. Of course, Aniruddhan had told me that he will not be coming on Monday because he's attending something else. And Wednesdays and Fridays, he has been coming always. Thomas Kurian and Adityan Ganesh. And maybe a few others. Okay. Take care. Good luck. See you on Wednesday.